In this lesson, we're going to cover hashing. First of all, we'll start with an overview. Then we'll look at hashing functions that are used in Ethereum, which is the keccak256 function. We'll dive into some basic technicals, hashing function properties, some real-world use cases, examples, and then a demo. So let's get to it. First of all, the hashing overview. So a hash function is basically any function that can be used to map data of arbitrary size to data of a fixed size. So how do you generate a hash? Well, you generate a hash, you take a piece of data and pass it through a hashing function. So as we can see below, the diagram shows a piece of data being passed into a hashing function and it spits out a hash, which looks like this. More on what this format is in a bit. So the hashing function used in Ethereum. So Ethereum uses the keccak256 hashing function. Keccak256 was originally designed as a candidate for SHA-3. Now you might see SHA-3 mentioned in the Ethereum documents and code, but actually it's keccak256. If you want to confirm whether your library is using keccak256, that is the same implementation as Ethereum, versus the SHA-3 implementation, then you can just simply hash an empty string and compare the output below. So when you hash an empty string using keccak256, you'll get the string C5D2460 and so on. And if you hash the empty string using SHA-3, you'll get the string A7FFC6 and so on. The hashing functions keccak256 and SHA-3 are very similar, but the Ethereum Foundation chose to move forward with keccak256. Basic technicals of SHA and hashing functions. So SHA stands for Secure Hashing Algorithm. And when you see 256 following that, that means it's the size of the hash that is output, meaning it is a 256-bit or 32 bytes value that is returned from the hashing function. A cryptographic hash function is a one-way hash function. Therefore, it's computationally infeasible to retrieve the input data if you only know the output hash. So given these properties, it is possible to quickly and easily identify any piece of data just by its hash value. So hashing properties. We're going to run through a number of different hashing function properties, and the first one is determinism. Determinism means that the same input data will always yield the same output hash. So let's take a look. Below we can see the string hello world being hashed using the keccak256 hashing function, and the output is a hash that starts 592FA743 and so on. If we hash the same string, the same input data again with the same hashing function, we will have the same hash string output. This works 24 hours a day, 7 days a week, 365 days of the year. No matter when you hash the string hello world using the keccak256 function, it will always yield this hash output. I could come back 20 years, 30 years, 40 years time and hash this string and it would still be the same value. So that's determinism. The next property is verifiability. It should be computationally efficient to generate the hash. This means that given that it's efficient to generate the hash, it's also efficient to verify the hash. So the hashing functions should be fast. If it was inefficient and slow to generate the hash, then it would be difficult and infeasible to verify the hash. So verifiability is an important property of hashing functions. The next property that we want to look at is something called non-correlation. So in a hashing function, for the input that is passed in, if you change just one character, then you will receive a completely uncorrelated hash to the previous hash that was generated, thus making it impossible to correlate hashes between different inputs. So let's see here we have the string hello world being hashed using the keccak256 function, and it outputs our familiar 592FA74 that we have seen previously. Then we go ahead and hash hello world, but notice this time we lowercase the w and we pass it through the keccak256 function. The output is completely different. There is absolutely no correlation between these two hashes that are output, despite the fact that the input data is only slightly modified. In this case, we just lowercased the w. So non-correlation is another important property of hashing functions. The next property is irreversibility. So it is impossible to take a hash and generate the original input. The only possible way you could do this is through a brute force search through all possible input data. So let's take a look. Let's take a look at this hash here. What is the input data for this given hash? The hash that starts here 5C2875AD and so on. What could possibly be the input data? Well, we can guess to be or not to be, and then we hash that value. It outputs D08CE38 and so on. Nope, that doesn't match. What about another guess? Let's say this text. Nope, that starts 8839. That's nowhere near this hash. That's wrong too. That text, no, wrong again. And so on and so on and so on until eventually you just get tired of it. Even if you wrote a computer program to do this, eventually it would just stop and it would never guess the hash. In other words, in order to brute force search to try to determine what the hash was generated from, what the input was, you would have to feed it every single piece of possible text that has ever been written since the beginning of history and any text that could have been written in the future. So basically it is impossible. The next property that we want to take a quick look at here is collision protection. So it should not be possible for two different messages or input data to produce the same hash output. So let's take a look at this. If we hash hello world and we pass that through a keccak256 function, we get this same hash as expected. If we hash then hello Mars or some other string, some other input, if the hash function returns exactly the same hash as some other input data, we have a collision. And this means there's likely something wrong with the hashing function. In this case, we are hashing hello world and hello Mars, and we end up with the same hash. There's something wrong. So that's collision protection. There should be not possible to generate the same hash for different input messages. Right, real world use cases next, which is data fingerprinting. So data fingerprinting is essentially the use of hashing to hash large bodies of text, perhaps in a database, to see if there are multiple data sources that contain the same data. I'll give you a quick example. Maybe I've written a document that I am concerned that maybe has been stolen or plagiarized. So I can take different data sources that are publicly available and I can hash certain parts of the data or documents within these data sources and then compare that with my document that I've been writing to compare if my document is in these other data sources. That's just one example of being able to search very large data sets to see if a particular data set is present within them without having to read every single line. You just simply hash the data and then compare the hashes, which is far easier. Another example is message integrity. So When you're sending a document over the internet, how can you be sure that the documents that are received by the third party are the same documents that are sent? And the answer is that you can hash the original document before you send it, and you publish that hash or share that hash with the recipients so that they can verify it. So let's take a look at that. Let's say, for example, I have a document that I want to send to my friend. This is the original document, so I hash it using the keccak256 function to produce this hash. I send the document over the internet to my friend. They receive the document, and then in order to confirm and verify that they have received the intended original untampered, unchanged document, they will also hash this document they received on their side using the keccak256 hashing function, the same hashing function, and then we just compare the two hashes. If they match, then we can be certain that the document received is the same as the document that was sent. Another example of real-world use case of hashing is authentication. So we've all been there when we sign into an application and we use our password. How does the system in the back end know that the password is correct without actually knowing the password? And the answer, of course, is hashing. So given a sign up form, such as this one, where you enter a username and password, the password is actually hashed, perhaps using keccak256, and then that will be stored in the database, in a user's database. The hash is stored in the database, not the plain text password. This is important for security reasons, but it's also important for the next step, which is when the user signs in. So now they come back to the site later on and they go to the sign-in form. The sign-in form, when it's submitted, hashes the password using exactly the same function, which, if the password entered is the same as the password used during the sign-up process, then that will yield exactly the same hash. And then the system can just compare the hashes with the hashes in the database. If they match, then we can know that the password entered was correct. Unique identifiers is another real-world use case. So when any content is hashed, it becomes easily, uniquely identifiable from its resulting hash. And this can be used in databases and distributed file systems such as IPFS. So let's say, for example, I have a document and I want to submit that document to IPFS, which is a distributed file system. Then when I do that, the IPFS network will return a content identifier. And that essentially is a uniquely identifiable hash of the content that I've uploaded. And then I can take that hash, I can store that, and then I can use that in the future to retrieve the document that I uploaded. And I know that when I'm using that hash to request the document, that I will be getting the exact same document back because it matches that hash. Right, let's take a look at a demo. So we're going to take a look at a demo using a website that has a keccak256 hashing function available to use. So let's go over to that now. This is the site here. It's on this domain. I'll link to it in the notes. And it's basically a website, utility website, that has a bunch of hashing functions that you can use and try out. And of course, we're here to try out keccak256. So firstly, let's just hash an empty string. Remember I said earlier that if you want to confirm that you're using keccak256, you could hash an empty string and check the resulting hash. I can see that that matches the hash that is expected from the keccak256, so that's confirmed. And now we can type in a string like hello world, and we can hash that, and we see the familiar 592FA74 so on. So it's giving us the same output as shown in the slides earlier. Note that we can lowercase the w and rehash, and we get a completely different non-correlated hash to previous. And of course, we can hash anything we want. Hello Mars, and we can hash. There's also this auto update key here. We can click that so that it will update the hash as we type. So that's just an example of how to use the keccak256 function using this utility. Now this text box is limited in size, but as stated before, you can hash any content you like using the keccak256 hashing function. You can hash an audio file, a video file, an image, a document, just a simple string like this. You can hash your new novel. You can hash the entire works of Shakespeare, or just a single play of Shakespeare, the entire Encyclopedia Britannica, etc., etc. You get the idea. Any content can be hashed, and it will always result in the same sized output hash that is uniquely identifiable to the content or the data that you input into the hashing function. So that's it for hashing. I hope you enjoyed this lesson. In the next lesson, we're going to cover and dive into more about how the blockchain works and run through some hands-on examples of that. So I'll see you there.